The first lecture video in this set is about magnetic fields of the planets. It is a transition from the subject of atmospheres to that of terrestrial planet geology. In order for a planet to be habitable in the long term, it will need a magnetic field to protect the atmosphere. The presence of a magnetic field tells us that the interior of a planet has at least part of it in a liquid conducting or metallic state. The rest of this lecture video set is about the basic principles of terrestrial planet geology. We'll look at how we know what's inside a planet, how energy flows from the hot interior to colder surface, and the four agents of changing a planet's surface: impact cratering, volcanism, tectonics, and erosion. But first, let's look at magnetic fields.
A magnetic field is a region of magnetic force that changes the motion of charged or magnetic particles. A planet's magnetic field forms a shield protecting the planet's atmosphere and surface from energetic charged particles coming from the sun and other places. The sun is constantly sending out charged particles called the solar wind into the solar system. These charged particles, protons, electrons, helium nuclei, are moving at literally 1,000,000 miles an hour. The solar wind fills the entire solar system out to about twice Pluto's distance from the sun. When solar wind particles run into a magnetic field, they are deflected and spiral around the magnetic field lines. Magnetic field lines are imaginary lines used to describe the direction charged or magnetic particles will move when responding to a magnetic field. The field lines are colored turquoise in the picture so you can see them, but they are actually invisible. Most of the solar wind gets deflected around the planet, but a few particles manage to leak into the magnetic field and become trapped in the planet's magnetic field to create radiation belts, or charged particle belts. One glorious effect seen when the solar wind interacts with the planet's magnetic field is aurora. Aurorae are shimmering light displays produced by molecules in the upper atmosphere. Fluctuations in the solar wind can give energy to the trapped charged particles in the belts. Particles with enough energy can leave the belts and spiral down to the atmosphere to collide with molecules and atoms in the thermosphere, the upper part of the atmosphere of a planet. These collisions excite the atmosphere molecules and atoms, bumping their electrons to higher energy levels. The electrons then release the excess energy as they hop downward back toward the atomic nuclei. The glow of the aurorae are the emission line spectra produced by the electrons in the rarefied gas dropping back down to lower energy levels. Here are some pictures of aurorae visible from Alaska and northern Canada. They change shape and intensity over time periods of a few seconds. The caption tells where the colors come from and how high up are those excited molecules or atoms. I like this picture because it shows the extent of sky that is covered by the aurora. Do you see the Big Dipper part of Ursa Major? The pointer stars in the bowl of the Big Dipper point to Polaris, the North Star at the tail end of the Little Dipper part of Ursa Minor. The two end stars in the Little Dipper are visible. The upper one, called Kocheb, was the North Star 2,000 years ago, but precession of the Earth's rotation axis has it now pointing really close to Polaris. The upper left part of the picture shows the familiar W shape of Cassiopeia. Here are some other aurorae that look like an electrical storm. Notice the reflection in the lake in the left picture. From space, you can clearly see that the aurorae occur in the very top part of the atmosphere, high above the highest clouds. The picture shows that the aurorae are especially visible in the ultraviolet band. The left picture shows the northern aurora band centered on the north magnetic pole off the northern coast of Canada, but offset from the geographic North Pole. Maybe you can pick out the outline of Greenland and Alaska, and just below the bottom of the aurora band are the Great Lakes of the United States. On the right is a picture of Jupiter, the king of the planets, has aurora larger than the entire Earth. The top left corner picture is Jupiter taken in visible light, and the top right corner is a picture taken in ultraviolet light. The loop is the electrical flux tube connecting Jupiter to its moon Io. 3 million amps of current flow in that flux tube. There's a white aurora spot where that flux tube hits Jupiter's upper atmosphere. Next slide. A magnetic field can be produced by circulating electrical charges. The magnetic field dynamo theory says that the magnetic field is produced by swirling motions of liquid conducting material in the planet interiors. Materials that can conduct electricity have some electrical charge that is free to move about. Such materials are called metallic and are not necessarily shiny solids like copper, aluminum, or iron. A moving charge will produce a magnetic field. The liquid conducting material in a planet's interior can be made to swirl about if the planet is rotating quickly enough. The faster a planet rotates, the more the material gets stirred up and therefore the stronger the generated magnetic field. If the liquid interior becomes solid or if the rotation slows down, the magnetic field will weaken. So in summary, what a planet needs in order to produce a strong magnetic field are 1. A liquid conducting metallic interior, and 2. Rapid rotation to get the conducting material moving about. For the terrestrial planets, plate tectonics may also play a role. Plate tectonics cools the planet's mantle because heat can be easily released, creating a large enough temperature difference between the core and mantle to produce convection in the metallic core needed to make a magnetic field. Earth's magnetic field is created in the liquid outer core made of iron and nickel. The inner iron-nickel core is solid despite its higher temperature than the liquid outer core because the pressures are so great. When the Earth was much younger, the entire core was hotter and liquid. The inner solid core is growing as the Earth's interior cools, but we still have at least a few billion years left of having a liquid component to the core. The fact that we do have a significant magnetic field tells us that the Earth must have a liquid conducting material somewhere in its interior. A better way to probe a terrestrial planet's interior is through seismology, explained
in another lecture video in this set.
Jupiter and Saturn have a large amount of hydrogen that is compressed so much that it forms a liquid. Some of that liquid hydrogen is in a supercompressed state where some of the electrons are squeezed out of the atoms and are free to move around and conduct electricity. This is liquid metallic hydrogen. This picture summarizes what we think the interiors of the planets are like. Uranus's and Neptune's magnetic fields are probably created in their mantles of slushy water mixed with ammonia and methane, labeled ice core here. The next picture shows a picture of the super strong, super deadly radiation belts around Jupiter, where charged particles spiral around Jupiter's magnetic field lines to produce the abundant radio energy we see with our radio telescopes.
The magnetic dynamo theory explains why Venus and Mars don't have strong global magnetic fields. Venus spins slowly, once every 244 Earth days, which is longer than a Venus year, and Venus does not have plate tectonics to cool off its mantle. There isn't a large enough temperature difference between the mantle and core to create the convective motions in its core needed for a dynamo. Mars has a rapid spin, but its solid mantle and liquid core are both relatively cool. Mars is small enough that it lost much of its internal heat. Larger planets take longer for their interiors to cool off than for smaller planets. The cooling time for how long it will take the interior to solidify is proportional to the diameter of the planet. The temperature difference between Mars's mantle and core is not large enough to create the necessary large-scale convection in the core for a dynamo. There are pockets of magnetism still remaining in some parts of Mars's lithosphere, but Mars has no global magnetic field to shield its atmosphere from the solar wind. So why does Mercury have a stronger magnetic field than Venus and Mars? Despite its slow rotation, one spin equals 59 Earth days, and small size, the interior should have cooled off to be solid by now, Mercury has a larger magnetic field than Venus and Mars. The magnetic dynamo theory explains the lack of global magnetic fields on Venus and Mars, but what about Mercury? Careful observations of Mercury's spin shows us that Mercury's interior is still partially molten. The Messenger spacecraft's measurements of Mercury's gravity field confirm it. So why is Mercury's interior still molten? Possibly a mixture of sulfur with iron lowers the melting temperature of Mercury's interior. Mars's core also has a significant amount of sulfur mixed with the iron, but for some reason, Mercury's core is able to sustain convection for a dynamo, while Mars's core cannot. Research continues. Stay tuned.